In this video, we will learn how to use Bordeaux-Hessian method in checking second order condition for a multivariable production function. The question is, the production function for a firm is being given as says Q is equal to 200 minus L square minus K square, and corresponding cost function is C is equal to 2L plus 3K. If the firm wishes to maximize its output for a specific level of outlay of cost is equal to 30, we need to find out the maximization problem for the firm. Second part is to find out the levels of capital and labor for which output is maximized. Third question is the second order condition satisfied? And last part is to find out the maximum output. Okay, so let's do it one by one. So for the first question, we are being given this production function. We want to maximize this production function subject to the production constraint. Okay, that means subject to the budget constraint. Our budget is, that is, price of labor is 2 and price of capital is 3 and total cost is 30. So we want to maximize our output, that is Q is equal to 200 minus L square minus K square. This is our production function. So we have a maximization problem subject to the cost constraint, that is 2L plus 3K is equal to 30. Okay, this is the solution for the first part. That means we want to maximize production function subject to this cost constraint. Okay, second part tells us to find out the levels of capital and labor for which Q is maximized. Okay, so for that, what will we need to do? We need to construct the Lagrangian function. And how do we construct the Lagrangian function? Let us see it by step. Okay, given this cost constraint, first step is to set it equal to 0. Okay, that means 30 minus 2L minus 3K is equal to 0. Okay, second step is, and let me write it, to multiply this resulting constraint by lambda, that is 30 minus 2L minus 3K is equal to 0. Let us multiply it both sides by lambda. So we have lambda here. Okay, after that we need to construct the Lagrangian function. Let's denote the Lagrangian function by U. Lagrangian function is formed by adding the objective function. And what is objective function? Objective function is our production function with the resulting constraint, which is formed by setting the constraint equal to 0 and multiplying it by lambda. Okay, so our Lagrangian function is formed by adding this objective function. Let me write it here. So our objective function is 200 minus L square minus K square. Okay, given this objective function, we add this resulting constraint, that is, we have 30 minus 2L minus 3K. Okay, now we need to check the first order condition. First order condition for maximization requires that we take the partial derivative of this Lagrangian function with respect to labor, capital and lambda and set them equal to 0 simultaneously. Okay, and solve them. Okay, so first order condition requires, first order condition for for maximum requires, we take partial derivative. Let's denote U subscript L as the partial derivative of this Lagrangian function with respect to labor. So derivative of L, here no L is involved, so its derivative is 0. The derivative of L square is minus 2L, so we have minus 2L. And here no L is involved, its derivative is 0. Here we have L, derivative of L is 1, so we are left with minus 2. Minus 2 into lambda is minus 2 lambda, and we set it equal to 0, or we can write it in this fashion: minus 2L is equal to 2 lambda. Okay, let us say this is equation first. Symmetrically, we take the partial derivative with respect to capital and set it equal to 0. This time we take partial derivative with respect to capital. Derivative of K square is minus 2K. Okay, Derivative of k is 1, so we are left with minus 3, and we have lambda multiplied. We set it equal to 0, which implies minus 2k is equal to 3 lambda. Okay, let us say this is equation second. Then take derivative with respect to lambda. Okay, so derivative of lambda is 1. No lambda is involved in the first three terms, their derivative will be 0. Derivative of lambda is 1, so we are left with 30 minus 2l minus 3k. Okay, this is not really necessary here. Okay, let us say this is equation third. Now what will we do? We divide equation first by equation second. Dividing equation first by equation second implies, so first equation is minus 2l, second equation is minus 2k is equal to, we have 2 lambda here, here we have 3 lambda, which implies lambda lambda cancel, minus minus cancel, 2 cancel, implies l upon k is equal to 2 upon 3, which implies L is equal to 2 upon 3k. Okay, after that what will we do? We simply plug the value of L is equal to 2 upon 3k either in this third equation or in our cost constraint. Okay, let us put it into the cost constraint function. So we can write it in this fashion, that is, we have 2 in place of L, we have 2 upon 3k, so 2 upon 3k plus 3k is equal to 30, which it becomes 2 to the 4 k upon 3 plus 3k is equal to 30. Okay, multiplying both sides by 3, so we have 4k plus 3 3s are 9k is equal to 3 30s are 90, which implies 13k is equal to 90, sorry, that means k is equal to 90 upon 13. This is the optimal value of capital we require. Okay, now to find the value of uh, labor, simply plug k is equal to 90 upon 30 in this equation. Okay, so let us plug here the value of k, which implies our L will be equal to 2 upon 3, the value of k is 90 upon 13, which gives us 3 ones are 360s are, so we get optimal value of labor is equal to so this is 330s are obviously, so 30 into 2 is 60 upon 13. Okay, we got the value of L and K for which Q is maximizer. Now the third part tells us whether the second order condition is satisfied. Okay, so for constructing the second order condition, or rather for checking the second order condition, we use the bordered hessian matrix, okay, method. So how do we construct a bordered hessian matrix? Let me show it here. Let us say H bar, this denotes, and let me write it here, you will get the idea. So bordered hessian is actually a matrix composed of the second order partial derivatives of Lagrange's function bordered by the partial derivatives of what we call cost function. Okay, and let me show how do we calculate it. So we have 0 here, then we have C subscript L, C subscript K, C subscript L, C subscript K. Okay, then we have U subscript LL. I will explain what exactly is meant by these terms. U subscript LK, U subscript KL, U subscript KK. Okay, so first we form this bordered hessian matrix. C subscript L, I have explained it. Bordered hessian matrix is a matrix which is composed of second order partial derivatives of the Lagrange's function bordered by the first order partial derivatives of cost function. Okay, and let us see what exactly is meant by each of the term. So C subscript L means the derivative of cost function with respect to L. So derivative, if I set it equal to 0, so it will become 2L minus 3K, sorry, 2L plus 3K minus 30. Okay, let us say this is our cost constraint. Derivative of L, derivative of L is 1, so we are left with 2. C subscript L is equal to 2. C subscript K, again derivative of K is 1, so we are left with here we are left with what we call 3. Okay, then so this is CLCK. Now U subscript LL means the second order derivative of second order derivative of this Lagrangian function with respect to L. This is the first order, so this is the first partial of Lagrangian function with respect to L. ULL means again differentiating with respect to L, so we will be left with minus 2. ULK means the second partially differentiating this function with respect to K. Since no K is involved, so derivative is equal to 0. Similarly, UKL, it will also be equal to 0 by Young's theorem. I am old, but Young's theorem is obviously young. So KL means, so this is U subscript K partially differentiating with respect to L. Again, no L is involved, its derivative is 0. Then we have UKK means the second order, that is partially differentiating this function with respect to K. So we are left with minus 2. Okay, let me see if I have cleared it. Okay, it is I guess so. We have 3K 3K. Okay, so here we again get minus 2. Okay, so then what is our border hessian? So our border hessian is being denoted by this, and we have 0 here. CL is 2, we have 3, then CK 2 3. ULL we got minus 2, ULK is 0, UKL is 0, UKK is minus 2. Now we need to, so this is our bordered hessian. Now we need to find out the second bordered principal minor. This is also called the second bordered principal minor because this is our minor which is of order 2 by 2 and it is being bordered by the cost constraint. Okay, so we call this, and let me write it here, H, this is bordered hessian, is equal to H2. Okay, so H2 is equal to H here. Okay, so this H2 is actually second bordered principal minor. That means we need to find out H2. The value of H2 will be H2. So taking determinant of this, so we have 0. Now deleting this row and this column, multiplying these two, so minus into minus is plus, 2 2s are 4 minus 0. I hope you know how to take the determinant. Then we have minus from the formula, that means deleting this column and this row and multiplying the resulting elements. So we have 2 into, and I am really sorry if I have done any mistake in calculating this step. So 2 2s are is minus 4, then we have minus 3 zeros are is 0, then we have plus from the formula, we have 3, this time deleting this column and this row and taking the determinant of the remaining elements. 2 zeros are 0, minus into minus is plus, so we have 3 2s are 6. So this will become 0, minus into minus is plus, here we will get plus 4, and let me write it here, plus 3 6 are 18. Okay, so we get H2 is equal to 22, which is greater than 0. Okay, So what is meant by this stuff? And let me explain it here. Here we got the value of since h2 is greater than, since our second border principal minor is greater than 0, when the second border principal minor is greater than 0, we say it is negative definite. Okay, we say it is negative definite. And negative definite satisfies the condition for relative maximum. Okay, if the second border principal minor came out to be greater than 0, we say our bordered hessian is negative definite, and negative definite satisfies the condition for relative maximum. That means second order condition is satisfied. Okay, so there are 2 3 things which I want to clear here. Okay, so here we have 3 by 3 matrix. If we have 4 by 4 matrix, okay, then we would have to check two conditions. Okay, that means we need to find out the second bordered principal minor and third bordered principal minor. Okay, I will not explain that very stuff here. Okay, so let us you know uh, solve it for other parts. So the last question is, what is maximum output? Simply plug the value of optimal value of labor and capital into the production function. Okay, so maximum output will be equal to, so our q will be equal to 200 minus L square, means 60 upon 13 square, minus K square, the value of K which we got here. Uh, did we calculate it? Yes, we calculated. That is 90 divided by 13 square. Okay, solve it by yourself. You will get the maximum value of Q. Okay, let me explain one thing here about the second order condition. Okay, if second border principal minor is greater than 0, it satisfies the condition for negative definite. Okay, and we have the relative maximum. If second border principal minor is less than 0, we say it is positive definite. Okay, it satisfies the condition for minimum. Okay, if we have, if the principal minors, and let me write it here, if we have, if h2 is greater than 0 and h3 is less than 0, if the principal minors alternate their signs from positive to negative, it is also negative definite. Okay, negative definite, it satisfies the condition for negative definite for maximum. Okay, if second border principal minor is greater than 0, third border, if all the principal minors are greater than 0, then we have fourth border. So we also say it is so greater than 0, negative definite. It also satisfies the condition for uh, a negative definite. It also satisfies the condition for negative definite, satisfies the condition for maximum. Okay, if if all the principal minors are less than 0, that means h2, h3, and similarly h4, if they are, then we say it is positive definite and they satisfy the condition for minimum. Okay,